This section introduces the central question of the book and its answer. Maeterlinck asked what governs here in the insect colony, and the structural answer is that nothing governs. The leaf-cutter highway, the weaver ant chain, the termite cathedral are all built by colonies with no supervisor and no blueprint held in any single insect. The chapter's move relocates the explanatory burden. The complexity that looks individual is actually carried by the interactions between simple agents. Self-organization, borrowed from physics, makes macroscopic order emerge from microscopic rules. So you never need complex insects to explain complex colonies. The book then inverts this for engineering. Model the natural mechanism first, then tune it past biology into an artificial swarm. Here is the catch. The chapter plants. Emergent solutions resist being programmed directly because the path lives in the interactions themselves rather than inside any one agent. This section explains why a colony needs no one in charge. Maeterlinck asked the question, the chapter exists to dissolve. What issues the orders? The answer is that no one is in charge. The termite mound, the ant highway, the parallel comb are fixed points of local interaction, not blueprints executed by a controller. A colony is a decentralized problem solver. Simple agents, simple rules, no global plan, and yet the macroscopic pattern stays robust and flexible precisely because it has no center to lose. The engine behind this is self-organization, macroscopic order emerging from microscopic processes, borrowed wholesale from physics and chemistry. The book's wager follows at once. If biology builds order this way, engineering can steal the trick. Every later chapter is one instance of order without an orderer. This section explains how an ant colony solves a shortest path problem that no single ant understands. A colony finds the shortest path to food without any ant knowing what shortest means. The objective lives in the medium, not in the agents. Each ant writes pheromone onto the trail. It walks and biases its next step toward where the pheromone is dense. A shorter branch is traversed more often per unit time, so it accumulates reinforcement faster, recruiting more ants, locking the colony onto it. That single autocatalytic loop reinforces what gets used by writing to a shared evaporating field is the chapter's primitive and the book's. Transplant it, and you get ant colony optimization for the traveling salesman problem and AntNet for live network routing. Evaporation is what keeps the loop adaptive. Without that forgetting, the loop fossilizes the first solution it ever found. This section explains how a colony with no memory becomes an optimizer, using the binary bridge as its smallest witness. Positive feedback over a shared modifiable medium turns memoryless agents into an optimizer. That is the whole chapter, and the binary bridge is its smallest witness. Ants drop pheromone, the ant only reads and reinforces locally. The shorter branch is traversed more times per unit time, so it accrues pheromone faster, so more ants choose it. Autocatalysis collapses the colony onto the short path, though no single ant ever compared the two. The medium does the integrating. The ant only reads and reinforces locally. This is what the chapter is for in the book's arc. It converts the self-organization thesis into a reusable algorithm template, ant colony optimization. It shows that template, solving a static combinatorial problem, the traveling salesman problem, and an online, time-varying one. AntNet routing. This section explains how division of labor arises in a colony without anyone directing it. Specialization appears without a specializer. Each agent carries one scalar per task, a response threshold, and reads a shared stimulus that climbs whenever the task goes unserved. Low threshold agents fire first, draining the stimulus before high threshold ones engage. Allocation falls out of the field, with no manager assigning anyone. Pull the active workers away and the stimulus rises until the reluctant ones cross over, so colony resilience is read directly off individual elasticity. Now let the threshold itself drift, lowered by doing and raised by abstaining, and initially identical agents differentiate into castes. Here is the chapter's move for the book. Division of labor is a threshold on a common scalar, and hysteresis in that threshold is memory, so specialization emerges rather than being designed. This section explains how a colony of workers decides who does which job, with nobody in charge. Each worker carries a private threshold for each task. It acts the moment the local task stimulus crosses that threshold. So, low threshold individuals soak up weak demand, and high threshold ones stay idle until the stimulus piles up. Division of labor is just the sorted consequence of a threshold distribution. Let doing the task lower its own threshold, and not doing it raise the threshold. Then initially, identical agents drift into specialists. The colony stays resilient because a removed worker leaves rising unmet stimulus that recruits whoever's threshold it next crosses. Here is the chapter's payload. This same private threshold rule allocates tasks in any multi-agent system. It is a market where the bid is a threshold and the price is stimulus. This section explains how one local ant rule produces global sorting, and how renaming the item it sorts turns the same rule into clustering and graph partitioning. A single local rule generates global sorting. An ant is more likely to pick up an item sitting among dissimilar neighbors, and more likely to drop it among similar ones. From this alone, you get global sorting with no global map, no item-to-item comparison, and nobody deciding where a cluster belongs. Positive feedback closes the loop. A growing pile of like items attracts further deposits, so order amplifies itself out of a random scatter. The chapter's move is denotational. Call the item a data point and its grid position a learned in two-dimensional embedding, and the ant rule becomes clustering. Call it a graph node and let spatial proximity stand for connectivity, and it becomes partitioning. One behavior, 3 readings, switched only by what the word item is taken to mean. This section explains the algorithm that Chapter 4 reads out of ant behavior. Each chapter of this book reads one algorithm out of a single ant behavior. The behavior in Chapter 4 is clustering. Workers pile corpses into cemeteries, and they sort larvae by size. The algorithm underneath is data analysis and graph partitioning. The generative move is the one that foraging and division of labor already taught. No agent sees the whole. Each agent only picks up and drops items according to local density. Positive feedback does the rest. A small pile attracts more deposits, so global order condenses from a purely environmental trace. Sorting is clustering that carries a similarity metric. Items left adjacent in the two-dimensional arena are alike, so the dynamics hand you a low-dimensional embedding for free. Here is the contrast with classical clustering. No objective function is ever optimized. This section explains how a fixed environmental template turns self-organization from a chance pattern into a controlled one. Self-organization alone places clusters wherever the snowball effect happens to nucleate, with both count and location left to chance. The chapter's one move is to compose that dynamics with a template, a fixed field in the environment that gates where deposition is permitted. The product keeps every emergent signature: snowball growth, multi-stability, and hysteresis, yet it lands a perfectly predictable pattern because the field, not accident, fixes the geometry. Biologically, the queen's pheromone gradient stamps the royal chamber's size to her body. Algorithmically imposing prespecified dropping zones restores parametricity to the Chapter 4 clustering. You fix the number of classes in advance. The primitive is to gate an emergent process by an external field, buying control without killing the emergence. This section explains how a template constrains a self-organizing process. Self-organization fixes a structure's form, but leaves its placement free. Clusters grow wherever the first seed happened to land, since the only rule is that large clusters attract more. A template removes that freedom. A pre-pattern already present in the environment, the queen's pheromone gradient, a temperature field, supplies a boundary condition, and the same snowball dynamics now run inside it. You keep the amplifying feedback, the multi-stability, the emergent quality. You gain a result that predictably traces the pre-pattern. The chapter's move is to superimpose an external field on a self-organizing process, pinning the 1 degree of freedom self-organization cannot set on its own, namely where. Algorithmically, that converts non-parametric clustering into parametric. This section explains how insects build nests without any blueprint and why that same dynamics describes self-assembly. No insect holds the nest's blueprint. The architecture lives nowhere as a representation. A wasp drops a brick when its local neighborhood matches a configuration, and that deposit becomes the next trigger. This is discrete stigmergy, where the half-built structure is the only program in past construction stages, the next act. Building is morphogenetic. Form is the fixed point of a local stimulus response rule. The plan is never copied from anywhere. Relabel which element is active, and the same dynamics read as self-assembly. From the viewpoint of the bricks, the agents are mere scaffolding. That symmetry is the chapter's lever. One rule coupling local pattern to deposit subsumes both Polistes nests and self-reconfiguring robots, and a genetic algorithm can then search that rule space for buildable forms. This section explains how complex insect architecture comes from a discrete rule table rather than from any plan inside the insect. The complex form was never anywhere inside the insect. It lives in the workspace. Each brick a worker drops, rewrites the local stimulus field, and that altered field is what triggers the next brick. Construction is its own instruction tape. The move the chapter turns on is making the trigger discrete, a finite table mapping each neighborhood configuration class to one action. So no pheromone gradient is required, no continuous amplification, no agent holding a blueprint. Read from the brick side. The same loop is self-assembly. Once form is just the fixed point of such a rule table, the rule table becomes a search space. Evolve the lookup, and you breed architectures. Morphogenesis without a morphogen. This section explains how a load too heavy for any one agent becomes movable through purely local action. A load no single agent can shift becomes movable when each agent does the same simple thing: push, pull, realign on felt resistance with no foreman assigning roles. The transported object is itself the coordination channel. Ants coupled through the prey sense each other only as mechanical force, and the group's pull self-aligns without any ant representing the whole. This is the chapter's wager for collective robotics, with box pushing as the benchmark. Decentralized transport needs no plan, only local force, sensing plus recruitment when one body stalls. Here is the surprise, the author's flag. Roboticists, Cube and Zhang, built the only convincing model of ant cooperative transport before biologists did. The engineered abstraction preceded the natural history theory. This section explains how ants coordinate to carry an object together. The carried object is the channel. No ant tells another where to push. Each ant's pull alters the forces every other ant feels through the prey itself, so coordination is read off the load rather than exchanged as signals. This is the same stigmergy threading every chapter of the book, now in a haptic register. Group size is never computed. Ants recruit while the item resists and stop the instant it yields, titrating effort against difficulty instead of measuring weight. That is the entire primitive. A swarm of identical, mute, decentralized robots needs to push a box together. The chapter's quiet jolt is that roboticists formalized this coordination before any biologist formalized this coordination before any biologist did. This part of the epilogue explains the one problem the book leaves open. 7 chapters ran the map forward, from local rules to collective competence. The epilogue names what stays unsolved, the inverse. Given a desired global behavior, you want to recover the individual algorithm that generates it. No analytic inverse exists, so you either enumerate billions of candidate swarms or you search the space against a cost function. That second move is the same one as training a neural network by tuning its interaction weights. It is viable only if the map from micro to macro stays continuous enough for genetic search to climb. Everything else. The author's flag sits downstream of a single asymmetry. How complex an agent must be, the high variance that bars finance, the missing time, aware benchmarks, all of it follows from one fact. Forward is demonstration, backward is engineering, and only forward has been solved. This part explains the single unsolved problem the epilogue names, and why the 7 chapters before it could not reach it. 7 chapters demonstrated one direction. Local interaction rules compose into flexible, robust, decentralized collective behavior. This is the forward map, running from the individual algorithm up to the swarm-level pattern. The epilogue's whole charge is to name what remains unsolved, and what remains unsolved is the inverse map. Given a collective task you want performed, find the individual rules that generate it. That inversion has no method. It has only search. You explore billions of swarms, or you hunt the space with a cost function and evolutionary techniques, betting that the mapping from rules to behavior is continuous enough to climb. It has the same shape as training a network by tuning interaction weights, made harder because the agents act asynchronously and anywhere. Inversion by search is the frontier, the constructive chapters set up but never crossed.